tonight's guest is Pat Slane, because we're here to celebrate Chandra. So let's welcome to the stage Dr. Pat Slane. First of all, let me just say, because I love this, he was my lab partner in grad school many, many years ago. But, you know, things don't change that much. It does sort of seem like yesterday. And so it's really a delight to have you back here after so many decades.
Back is the wrong word because it's the first time I've ever been here. But
That's true.
It's great. It's great to be here in the lab together again. Well, thanks a lot. As I said, it's the first time I've ever been here to Griffith. It's really very cool. I'm here to tell you a little bit about the Chandra Xray Observatory, which is celebrating its 20th anniversary. That's what it really looks like. And so let me tell you a little bit about what Chandra is, and then give you some very quick highlights of what has gone on in the first 20 years that we've operated the mission. To start with, as Laura said, we have a number of great flagship missions flown by NASA that are referred to as the Great Observatories. They started back, the concepts of them started back when we were in graduate school, actually. And Hubble is one that you all know and have heard of a lot. It is still operating. The other four, the Compton Gamma Ray Observatory on the left there, is not operating anymore. That operated for a while and then re-entered the atmosphere. Spitzer you just heard about and we'll hear more about, and then Chandra. Chandra, well, let me point to the little temperature scale on this plot. Gives a basic idea of where these things operate in terms of the energetics of the things that we're looking at. So Spitzer looks at things that tends to be cooler, dust, cooler stars, etc. And then as you go up in energy and temperature, the emission from the objects moves up higher in the energy scale of the electromagnetic spectrum, up towards the X-rays. And so Chandra operates in that X-ray band. And you might ask why we would look there. Well, as I'll get to as we're going through things, there's a wide variety of things that emit in X-rays, particularly things that are exceedingly hot, exceedingly energetic, explosive, and some of those things can only be seen in X-rays. And there's a little list of things there that we can look at, including ultra high density objects like neutron stars, energetic jets coming from black holes and such, but also more common things, including the comet that you just heard about coming to us from outside the solar system, which Chandra's going to look at in December.
Oh, very cool.
Yeah. So an important thing to know about Chandra and X-ray astronomy in general is that it's not a very old field, and the reason it's not a very old field is that it couldn't happen until we could go into space. The plot that's shown here is an indication of how far down through the atmosphere towards the Earth radiation across the magnetic spectrum can reach. So in the visible range, which you can see in the yellow and green and blue lines, of course, the radiation reaches us all the way down to the Earth. Similarly with long wavelengths in the radio band, but you can see over to the right where the X-ray band resides that the radiation does not penetrate very far down. It gets absorbed in our atmosphere. So unless you can put something up to around 200 kilometers above the surface of the Earth, you're not going to be able to see the X-rays from something coming from out in space. So we couldn't do that until we could actually launch things up on rockets. That means that the field was only invented in the early 1960s. And in fact, the way it was done was that Riccardo Giacconi here, another Nobel laureate in physics, took 3 Geiger counters that are sensitive to radiation, put them together in kind of a group like this. They rotated around. They launched them up on a rocket that went up to about 285 kilometers, something like that. Stayed up for a total of about 6 minutes. They were looking to see if they would see any X-rays from the moon, actually. And the plots that you see on the lower left is a plot of what these counters saw as they were rotating around across the sky. And you can see that there's a big peak in one direction. There's a little blip there. That's the moon. They did see it. And then there's that broad, bright region in the south-southwest, which is in the direction of the constellation Scorpius. This was the first X-ray source ever discovered in the constellation Scorpius, so it's called SCOX-1. And we now know that it's actually a binary system with a normal star whose material is falling onto a ultra-compact neutron star. And that matter, as it's falling in, is getting very, very hot and glowing in X-rays, and that's why we can see it. It's a very, very bright X-ray source. This happened in 1962. You can see the publication date, December 1st, 1962. Upon the discovery of this, Riccardo Giacconi and his colleagues went to NASA and said, we needs to have, 1963 proposal, we needs to have a 12, did it say 12 feet? A 4-meter telescope. We need a giant X-ray telescope that's 30 feet long. We got to mount this thing into a rocket and get up into space so that we can have a gigantic X-ray observatory to look for more of these things. Now, this is audacious. This is like your kid coming in from the backyard and saying, I found a bunny. I put it around a blanket. I put a lamp on it. We're studying how it's interacting. We need the San Diego Zoo. NASA said no. They gave some smaller and very important X-ray observatories that were funded and that did fly. They went back in 1976 and put together another proposal that said we want a 1.2 meter X-ray telescope to fly into space. The general diagram looked sort of like this. And if you compare it to their original proposal, it looks awfully similar. The same big mirrors separated by 10 meters from a set of instruments in the back side. And that is a schematic of Chandra. So that's actually how it came about. The very interesting part about how Chandra operates has to do with its mirrors. Photons that come into a mirror the way a normal telescope would see them don't actually reflect well. In X-rays, they have to glance off of the surface of the mirror. If they come straight in flat to the surface, they just get absorbed. They have to glance off like a stone skipping off of water. And so we build these shells of telescopes, these cylindrical type mirrors, and the X-rays glance off of them and then bounce way back to a camera in the back area. I didn't think to bring this, but an interesting thing about these is that because the mirrors are essentially shaped like cones like this so that the X-rays can skip off of them, if I point that telescope at you, you can all see that it's got a giant hole in the middle. Most of the area is actually empty. And so you fill it up by putting nesting more smaller telescopes inside. Chandra has 4 such mirrors. That's a difficult thing to do to get those mirrors to focus X-rays. It's hard to keep those shells held in a very, very firm manner so that they will create a good image. The surfaces also have to be extremely smooth because when a surface is rough, it will scatter the light. And the surface has to be smooth, sort of on a scale of the wavelength of the light. So Chandra, to have exquisite quality mirrors, had to be polished to a quality where the roughness was small on the scale of X-ray photons, which is only angstroms in size. And
just for comparison, can you tell me what else is angstroms in size?
The other thing that is angstroms in size is atoms. And so it has to be polished to a point where it's not really bumpy on too much more than the atomic level. A bit more, but not much more. Now, how do you do that? Well, you get a you get a big cylinder of glass, and you take some of the glass off the outside so it's not so heavy. But then you start polishing the inside to an extremely high quality. And the process consists of, as my colleague Andy St. George explained to me one time, you polish it until you run out of money. And, then you coat the inside of it with a precious metal. We used iridium for Chandra, which helps reflect the X-rays better. We mount those mirrors. We put them into a spacecraft. So this here is the spacecraft, and it holds the mirrors. Way on the other side is where the cameras that can detect X-rays go. The big long thing in between is just the bench that holds them apart. We strap a rocket onto the, I'm looking this way, we strap a rocket onto the backside for reasons I'll explain in a minute, load it into the space shuttle bay. It's the longest anything that's ever gone up in the space shuttle. And then
30 seconds.
It was launched.
And then pray.
and then you hope it all goes well. It was launched on the Space Shuttle Columbia, which was the first one that was ever commanded by a woman astronaut, Eileen Collins.
12.
It was
11,
deployed into
10,
space.
9, 8.
I'll pause.
7, 6, 5, 4, 3. We have a go for engine start. 0. We have booster ignition and liftoff of Columbia, reaching new heights for women in X-ray astronomy.
Columbia is in the roll. We've got a fuel cell gate number 1.
Roger, roll. Columbia, we're looking in.
Nighttime
And then
launch,
after
I
that,
see.
yes, so it was a nighttime launch. It was really spectacular. Two other interesting things about it. It was deployed by Katie Coleman. So another reason that we have women in STEM posters up here, because Chandra was delivered by Eileen Collins and gently nudged out the door by Katie Coleman. Another interesting thing is you may have heard right after the launch that Eileen said something about fuel cells, something or other, and people on the ground said, Roger, we're hearing about that. Right after the launch, right when you heard that, the panel turned all red in the space shuttle because there were several anomalies. It all sorted itself out within 15 seconds, maybe faster than that. So nothing was wrong, but totally impressive to listen to them under that action. So this is what happens with Chandra. That it gets pushed out of the shuttle bay. As I said, it had a big rocket on the back. They back away from it and then fire that rocket, and that sends it into a very highly elliptical orbit. It's in an orbit that, at its largest distance, takes it about 140,000 kilometers from the surface of the Earth, which, for reference, is about a third of the distance to the moon. It goes around in about 64 hours. And we take data with Chandra. It's very far away, so to get the data back, we have to use very, very large antennas on the ground to capture it. We send the data to the Deep Space Network, which is an array of big radio telescopes that are used for interplanetary probes and other things. There's a series of 3 of them around the globe. This one is in Goldstone, California. There's also a set in Madrid and some in Australia. The data come from there immediately to our operations center that we operate in Cambridge, Massachusetts, where we confirm that everything is okay with the spacecraft that we just got the data from, check everything out, and then send commands back up to tell it what to do next. Okay? So that's how it all works. Now, some highlights about things that we have studied with Chandra.